So last time in class, we introduced this concept of a moment. And the idea is we're using kind of the mathematical definition of a moment, or the, I don't know, physical definition of a moment, to relate back to statistical properties or metrics of distributions. And we talked about the first moment of a distribution of a distribution. And what was that first moment of the distribution? The mean. And we had a lot of ways of defining the mean. Mathematically, we called it the expected value of x. So x is our random variable. The expected value of that is equal to this first moment. We defined it a lot of ways. So it can be called mu, and that is from a population or a theoretical parameter of a distribution. Or if it's based on a sample, it's x bar. And then mathematically, there's a couple ways. So if we're kind of thinking of a theoretical distribution, then we can calculate the expected value using that fairly simple equation, which ends up being the same as identifying the location of the centroid of a distribution on an x-axis. So if this is a PDF of our variable, our random variable, probability density on the y-axis, the range of values that a random variable could take on, then this distance, a little bit too far there. This distance along the x-axis, we can think of as the distance to the centroid. And that is mathematically defined as, which we'll just say expected value of x is equal to the integral of x times the distribution function dx. And I posted an example of that. No, did I? Anyway. I think I posted an example. I posted an example that gives us kind of the finding parameters of a distribution. So there's a video example of using these kinds of equations. The second moment, and then we're going to do the third moment. Just to review the second moment. Of course, if we have a sample, sorry to go back here. If we have a sample, then we can simply just take the sum of our values, right? And divide that by n. We've all done that before. And then last thing I'll write up here, though, is this is for a continuous variable. And for discrete, do you remember what that was? All we did is we took each value that x can take on and multiply it by its probability mass or relative frequency. So if we have this distribution of the sum of dice rolls, what's the average value? You take, okay, 2 through 12, and then you multiply each of those values by the probability of seeing those values from the theoretical distribution. So you can go back and look at your notes for that example that we did. The second moment is the variance. Which we define as sigma for a population, or S for a sample. Computer science student. I love that. But they knock. Like, why can't I get in here? White. Class in session. And this was defined as, oh, sorry, variance is sigma squared. Apologize, guys. Remember, the standard deviation has the same units as x, and we have to take the square root of it. That's because the variance of x is equal to the square root of x minus mu. So all we did was we plug in the difference between each observation and the mean into this parentheses and then multiply it out. Squared, sorry. So we square it because that allows us to, it does two things. One, it weights really far values. It gives them kind of, it's squaring that distance more, so it gives it a little bit more weight. And it also gives you an absolute value, essentially. So the variance doesn't tell you if it's negative or positive, it just tells you if it's how spread out the data are. And then I didn't give you this formula last time, but I just want to put it here, and that is how to calculate from a sample. And we'll get into sample statistics a lot more later, but the variance of x for a sample is equal to the sum of the observations minus mu squared all over n. I equals 1 to n. And notice that I put in mu here. So this is when we have a population metric. We don't have time to really get into what is a population, what is a sample, but I'm introducing it now. And further down the road, we'll talk about that more. But just to have it in your wheelhouse, if it's not a population metric, if it's just based on a sample, x bar, then we divide by n minus 1. And this is basically a, it's called an unbiased estimator. That n minus 1 corrects for bias that could result in skewing the values of the variance based on a small sample size. There's a lot of math behind it, which we won't get into. Okay, last moment that I want to tell you all about. It's the third moment. Does anyone listen to classical music, the third movement? I don't actually, but I just know that's a term that people use. You know, the concert's been going on for 2 hours and now we're in the third movement. The third moment is called, we call skewness. What's that? It's what happens when your hand does what your mouth is doing and not what your brain wants to do. It's called skewness. And I'll just draw it out first and then we'll just write it out mathematically. So skewness, if we have a distribution that's perfectly symmetrical, which is exactly what I'm going to draw up here, and we'll denote skewness with the symbol gamma. So in this case, if it's perfectly symmetrical, it means it's not skewed one side or the other. In this case, gamma is equal to 0. But if we have a distribution that is skewed, in this case, we call this positively skewed. And the reason we call it positively skewed is that it's got a thick tail towards larger values, meaning there's a higher probability of seeing more extreme values. This is gamma is greater than 0 or positively skewed. And then we have negatively skewed. So negatively skewed. And that means smaller values or negative values are, there's more of them. They're extreme than based on a symmetrical distribution. Can you think of something that could be positively or negatively skewed, a distribution of a random variable? Let's think of something that's symmetrical. What is something that you have equal likelihood of seeing greater than or less than a mean value? The normal distribution, right? Heights? Probably. I don't know. Yeah, probably heights. Average height. Some people are taller, some people are shorter. That probably makes sense. I think in the video that we looked at, heights were normally distributed approximately. Yeah. How about something that's not normally distributed, where you have a lot of people or a lot of things centered around some area and then a lot of extremes? Salaries. That would be a skewed distribution. Yeah. That's why we talked about using the median to describe it. So everyone's hovering around, I don't know, 50, 60, 80 range or something like that. And then you've got those executives or whatever, people making money, a lot more money. So that would be something that we would say is positively skewed. I know I wrote that in red. Maybe that's a little counterintuitive, but it's hot. Got those hot salaries. All right. So we're not going to like do the calculus here, but the calculus would just be x minus mu to the third. You just kind of keep going up. Well, I'll just write it out really quickly. But so gamma is equal to x minus mu to the third. It's just, you can see there's a pattern here now. Squared was the variance, cubed is the skewness. This is not something we're going to necessarily do, but I just want to show it to you. And then if we're going to do this for a sample, so G would be the sample statistic based on just like a sample of values statistic. This one's a little funky. But I'm going to give it to you. We've got the sum of x minus mu to the third all over the standard deviation to the 3/2 and times n. This is when the population statistics are known, meaning you have a really big data set, or you just know that, you know, globally that this thing has a mean of this and a standard deviation of this. But if we just have a small sample size, then G is equal to this really complicated thing, but it's good to know what's behind it. And this is our kind of unbiased estimator for small sample sizes. There are functions that will calculate skewness for us. And if you go into Excel, I think still they do this. They ask you, is this based on a population? Are population statistics known or unknown? And so the Excel functions will ask you that, and they'll use these different equations based on your answer. So that's a big one. Notice that the definition for the variance is in here. That's part of this over there. That's it. What's that? That's it. I'm sorry, I didn't hear you again. You don't like that at all? Yeah, I mean, I might ask you to do that, but there are built-in functions that'll do that. So, and then finally we have the skewness coefficient. So similar to the coefficient of variation, CV was equal to sigma over mu, normalizing our standard deviation with the mean so that we can compare across different things. I gave you the example of different rivers, but you can imagine if you want to calculate the coefficient of variation for salaries in the US versus say Mexico, right? The mean of the salary in Mexico is probably gonna be different than the US. So you could divide by the mean salary and compare the coefficient of variations. So the skewness coefficients, which I don't know a symbol for that. We just call it skewness coefficient. And that is going to be gamma over sigma cubed or G over standard deviation cubed.